Good afternoon, all. Welcome back to ICTEA 2025. I hope you had a refreshing break and are now ready to engage in the upcoming technical session, which promises to be both insightful and enriching. We are fortunate today to have Dr. Urbi Chatterjee with us. I'm sure that the knowledge shared today will enhance our professional skills. Without further ado, let me introduce our esteemed speaker, Dr. Urbi Chatterjee. Dr. Urvi Chatterjee is an assistant professor in the Department of Science and Engineering, Indian Institute of Technology, Kanpur. She received her MTech degree from ISM Dhanbad in 2013 and PhD from IIT Kharagpur in 2020. She has also worked in industry for 1.5 years. Her broad area of research is hardware security. She currently works on physically unclonable functions, security analysis of approximate computing hardware, timing side channel attacks on network on chip architecture, acoustic side channel attacks, etc. We are truly privileged to have her with us today. Without further delay, I request Dr. Urvi Chatterjee to begin today's session. Over to you, ma'am.
Okay, so I think we can start now. Okay, so as I I would like to thank the head of the department, CAMK, for this nice introduction. And good afternoon to all of you. Thanks for joining the session today. So today we are going to talk about hardware security, which has emerged in last 15-20 years, around 15-20 years in India recently. So today we were going to talk about four topics in which our lab settler at IIT Kanpur we are working on, and what are the recent progresses that we have made in this domain. Okay. So I'm Ruby Chatterjee. I have a small lab in IIT Kanpur named Secure Embedded and Smart Pins Laboratory, and we are mainly funded by Department of Computer Science and Engineering and Cybersecurity of Cyber Physical System Innovation Hub, which is also situated in IIT Kanpur. So we work on a different research area. I will name a few for your knowledge gain. Basically, we work on secure and reliable approximate computing. Hardware perspective, we work on physically unclonable function-based authentication. We work on machine learning attacks on physically unclonable function, UAV security, far field side channel analysis of mixed signal chips, screen reading tempest attacks, acoustic side channel attacks on embedded system, network data remnants-based side channel attacks, timing attacks on network on chip architecture, hardware acceleration and side channel attacks on post-quantum cryptography, machine learning-based countermeasure against side channel attacks, VLSI for cryptography and hardware security model. And we are also working on biochip security in collaboration with New York University. So my team here, I joined IIT Kanpur in March 2021. So in this upcoming March, I'll be covering almost 4 years here. So then in my team, we have Professor Devukri Basuroy, who works on basically post-quantum hardware. Then we have our PhD students, Oswa, Nilofar, Dipesh, Vishesh, Suraj, and Anjali. Many of them are PMRA fellow. Oswa is a international PhD scholar, and Dipesh is a TCX research scholars. And any kind of hardware setup or hardware laboratory needs a lot of funding. So I would like to thank TCS, PMRF, CITRE Hub, MIT, Semiconductor Research Corporation, DRDO, and Ministry of Science and Technology for funding our research. Now, this is a small glimpse of the activities that we do and the topics that I have actually just told you about. So we have, a lot of side channel attack and countermeasure development set up in our lab. Oscilloscope, FPGA boards. We have a lot of cameras and drones and acoustic side channel setups. We have a lot of EM probes to extract EM radiation from mobile phones. We have this big antennas to extract signals far away from the chips. and also we work on biochip securities, which the main lab is in NYU Abu Dhabi, but we actually collaborate with them for developing unclonable function, physically unclonable function out of the biochip, so that nobody can replicate those chips. But we will cover only 4 topics today, very slowly, because I think this particular topic is very new to all of you. Uh, but I would like to know whether you are aware of hardware security or not. Is anybody working on side channels or logic locking or puffs and all in your college? Anybody is aware of it? Okay, I guess no. So let us understand what is hardware security and what are side channels. So suppose Alice and Bob are currently talking to each other. Okay, so if they over a network. Okay, so if they talk in plain text, anybody can tap the channel and get what they are talking about. So now what happens that they say that okay, we want to create a authentic channel between us that will give us confidentiality, integrity, and availability of the information. So they implement a cryptography block box at both sides, and whatever information Alice wants to give to Bob, it encrypts the data, send over an insecure channel. Bob decrypt it and get back the original information. Now the target of the attackers is to tap in this secure channel and try to get some information. Now, a theoretical cryptographer, what they do is that they try to make this cryptography box mathematically secure. So the people who works on RSA, ECC, AES, DES, the mathematical foundation of this cryptographic algorithm, they try to make the algorithm mathematically secure so that the attacker has to do brute force. Okay. Now comes this unfortunate people like us. We are hardware security engineers. So what we do is that the same algorithm, the AES, DES, RSA, or ECC, we write the hardware module for the same. Okay. So what we mean by hardware module? This is very important to understand. Today, every one of you are in front of a computer. Okay. So in this computer, you have a general purpose processor. Okay. So this processor can understand whenever you are writing something in Notepad. It also can understand when you are playing a game. If you are watching some video in YouTube, or you are doing Facebook or Instagram, right? So what we do is that whatever be the application, this application software, the assembly code for assembly code, or the final machine code is converted in such a way that they lies into the instruction that this general purpose processor understand. Okay, so whatever application software you run on the top, finally the instructions for running the software is needed to be understandable by the general purpose processor. So it has a specific set of instruction, and your program has to lie under it. But when I need a specific application, so where I do not need my processor understand all types of application, I just need my processor to understand a particular application. Okay, so then this hardware security engineer create an application specific integrated circuit to do a specific job. Okay, so for that, what is the advantage of this? If this particular co-processor or particular hardware module is doing the same job, then it is very fast compared to a general purpose processor. Okay, so now why do we need faster application of cryptographic algorithm? The reason is today you press a like button in your Facebook app. This will be encrypted first in your mobile and then go to the Facebook server. So whatever communication you do with server based application, they all first gets encrypted in your mobile phone and then go in the insecure channel. So instead of having a C or Python implementation of a cryptographic algorithm, we generally go for hardware implementation or hardware module for the same. So whatever code I will write for an AES or ECC or RSA, they will be looking like this. So a gate level and gate and register design, or a digital circuit for doing the same calculation that we can do for a C by writing it in a C or Python. Okay, but what is the advantage? We can implement this particular design in a FPGA board or in a ASIC chip, and this particular hardware will do only that thing. So if it is calculating ECC, or it is calculating AES or RSA, it will always only do that. It will not understand your game or a Facebook or a notepad. They will only understand a particular AES code that is running in this particular hardware. Okay, so as a result, hardware designs are very harder to make, but they makes the application very faster. Okay, so when we do this, uh, what happens is that now the attacker does not try to break the algorithm mathematically. Okay, because the mathematics has been always already proven to be secure by the theoretical cryptographer. But when we run this particular algorithm in hardware, what happens is that it draws some power. Okay, so by the way, whenever you are not understanding anything, please interrupt and ask question. Okay, so it will draw some power. Okay, it will create some noise. It will take some time to do this realization of this digital circuit. Okay, it will radiate some electromagnetic emanations. Okay, these properties of a hardware execution are called side channel. Okay, so suppose we have a hardware module for where I'm running a plain text, AES implementation, and which is taking a plain text and giving me the ciphertext. So it will draw some power, or it will radiate some electromagnetic radiation, and there are tools to capture those information. Okay, then there can be timing variation among different parts of the program, or there can be different patterns of cache hit or cache miss when I am running a particular algorithm. Okay, and then comes another kind of thing which we call as fault analysis or fault attack, where I can introduce a clock glitch or a power glitch. Yes, I think there is a question. Let me see first. Okay, it's not a question. That's anyway. Okay, so let's go back. Yeah. So here I was. So you just interrupt me whenever you do not understand. Okay. So what we do is that in fault attack, suppose I have a AES algorithm running. So generally in AES there are 10 rounds, and in every round we repeat some specific functions or specific operation. Okay. So what happens? The output of a particular round go to the input of the next round. So we basically use the same hardware 10 number of for n number of rounds. Okay, so whenever we are running one round after another round, we actually save the intermediate values in a register. Okay, and then once this n number of rounds are done, then we get the ciphertext. So an attacker can actually introduce some timing glitch or clock glitch or a laser beam to alter some of these intermediate register values. That as a result, what will happen is that there will be a change in the ciphertext that we get. Okay, so the faulty ciphertext that we are getting now and the correct ciphertext that it was supposed to give, can actually, the difference between them can give us information about this intermediate state. Okay, and this information about the intermediate state can help us to get the secret key. So whenever we work on security or privacy, what we assume is that we assume that we know the algorithm, we know the mathematics behind the algorithm, we know the hardware design of the algorithm, we know what are the plain text, we get what are the ciphertext. Just one thing is unknown in this whole setup is the secret key. My algorithm should be strong enough so that the attacker, having all these knowledges, seeing this plain text ciphertext pair, cannot gain the knowledge about the secret key. Okay, so if sometimes we found comments in many agencies is that I will not tell in public that what particular encryption algorithm I am using. Okay, then will my network will be secure? I would say for a certain time, for a certain time it might be, but not really. Okay, because when you have a big organization, there can be many insider attack, or the kind of ciphertext that it is generating. Like for example, AES can only create a 128, 256 or 512 byte ciphertext. Okay, so if I have the ciphertext and plaintext pair, and we have this kind of side channel knowledge that I just talked about, I can run the side channel analysis for 128, 256 and 512 byte plaintext ciphertext pair, and I can find out. Okay, so the variation of these cryptographic algorithms are not much, and the number of cryptographic algorithms are also not much, because the number of secure algorithms that we can implement are very less. Okay, most of the symmetric ciphers that were there, like RC4 and all, they are broken now. We in Wi-Fi module that we use, the Wi-Fi communication. Initially, they used to use RC4. Okay, but they are not good enough now. In the right now we are using AES 128 in Wi-Fi protocol, like WPA, WEP, WPA2 and all. So there are very limited choice of cryptographic algorithm that you can use, and then knowing that, you can actually do some brute force and break this algorithm. So this is the basic fundamental thing from where hardware security started. That whenever we are implementing cryptographic algorithm in hardware, what are the way that you can break this cryptographic algorithm without actually breaking the mathematical foundation of the algorithm. Okay, so this is where hardware security was originated. Now it has expanded to very different dimensions. Okay, we will cover four of them today, just four of them. But yeah, there are a lot in hardware security that is happening right now, and you can explore many of them. So today we are going to talk about something called acoustic side channel analysis. We actually published this particular paper in Journal of Cryptographic Engineering last year, 2024. So what is acoustic side channel? We just shown timing side channel, EM side channel, power side channel. So what happens is that in our hardware, the piezoelectrical and electrostrictive effects of the material used in the capacitors result in the capacitor interelectrode to vibrate, causing a chain reaction. So this vibration is transferred from this interelectrode to the capacitor terminals, from there to the shoulder joint, and finally to the PCB, causing something called singing capacitor phenomena. And why these capacitors are very important? Because the registers that I was just talking about, where we actually in an intermediate way we store our results of the calculations of the cryptographic algorithm, they are made of nothing but these capacitors. Okay, so whenever there is a change of, or there is a bit flip in these registers, the vibration happens in the capacitor, and it creates this inaudible sound. You and I cannot hear it. It's beyond our hearing range. But currently you are in front of your computer, and your computer is actually generating a lot of inaudible noise to human ears, and these can be used to profile your computer. Yeah, it's serious. It's a serious business that we're talking about here. So there are work by famous researcher Adi Shamir, where they have used this acoustic side channel and EM side channel to break your PGP secret key, the secret key that you use in your Gmail email services. Okay, just using EM and acoustic side channel, it has been shown that those key can be retrieved. Okay, so these are terrible. We most of us have no knowledge about them, and as a result, attackers can actually exploit this information to get knowledge about your usability or your privacy. So today what we are going to do is that, as I said, that this electrode vibrate with current, and this dielectric ceramic expands with the electric field and contracts the perpendicular to it. Now this metal end caps and shoulder joints vibrate. That is finally make the PCB also vibrate. So now in our lab, when we started the research on acoustic side channel attack, we take this small stethoscope. Okay, so we can hear the sound of our heart using this stethoscope, but normally when I'm sitting, I cannot hear the sound of my heart. So we use this stethoscope to understand the heartbeat of a microcontroller. Okay, so what we did, our aim is to build a disassembler to extract the intellectual property code or observe the side channel behavior of a known code in a device that, and then directly use it to detect any malware. So what we will do in this setup is that we will use this stethoscope to understand what are the codes that is running in the microcontroller. Okay, now we can make it a profile that suppose I am running a certain set of code in a microcontroller and sometime an attacker hijack my microcontroller and try to run a malware code. So this particular stethoscope can actually capture that the signature of the other codes that are running in terms of the malware, and can tell me, okay, see, there is a difference in the acoustic signature right now in the controller, so you must be aware that there is something else happening and not what you intended to run into the microcontroller. So this is our hardware setup. What we did is that, see, this is a small, this green part, it's an Arduino board. It has Atmega 32 microcontroller. What we did, we actually put some weight and some clay and uh, attach the that stethoscope front part uh, into the Arduino board. Okay. Now the other part from where we can actually hear the noise or hear the sound, that part is connected to this Bluetooth speaker, and this Bluetooth speaker is recording the noise and sending it to this my mobile phone. So I'm recording whatever this Bluetooth speaker is collecting from the other part or the end part of the micro stethoscope into a mobile phone wirelessly. Okay, so now what we did, first what we tried is that we keep the Arduino board on and off. Okay, so what we did, on off, so we get something like this. Okay, but these were in frequency domain signature. So then when we converted it into a time domain, we get clear signals like this. So these parts are on part, these parts are off part. Okay, so we can understand that when my Arduino board is on, the acoustic signature of the board is something different from when the microcontroller, the Arduino board is off. Okay, so now from there we try to see that, so we are getting 100% accuracy into understanding the state of the Arduino board. Okay, so now what we did, the target is to understand the acoustic signature of um, uh, every single instruction that is there in the Atmega 32 microcontroller. So what we do, we create a assembly language code where we started the code with no. No is no operation. Okay, it's a instruction that is there in every processor, be it a small microcontroller or a GPU or a CPU. Okay, and then between two no operation, we give the single instruction COM R16. That means take one's complement of whatever is there in register 16. Okay, so we take this particular instruction, covered it with no in the front, in the end. Why do we give this no operation? Because we know that the signature of this no operation will be different from the signature of the COM R16 operation. Okay, so for every instruction that is available in Atmega 32 microcontroller, we create profiles, acoustic profile for every single instructions, like this: no instruction, no, and we take multiple traces, and make it an average. Okay, so we understand that once we have different signatures of the instruction, we found that we can actually clearly differentiate between these instructions. Okay, So once that is done, what we have seen is that the acoustic signature are majorly divided into four parts, or the patterns are majorly divided into four parts. Now, what is the basis of these four parts? Let us discuss that. It's the most important thing. So the instruction that are there in the ATmega 32 microcontroller are of four categories. First category is the instructions that are completed in one clock cycle. Second, the instructions that are completed in two clock cycles. Third, the instruction that are completed in three clock cycle. And fourth is the instructions that are completed in four clock cycle. Now, complicated instruction like multiplication or division, they take more clock cycle than a simple complement. Okay. Similarly, the load and store operations in memory and instruction associated with operations takes more time, that is more clock cycle than the single clock cycle instructions. So in the acoustic signatures, we can clearly differentiate between the instruction that are single clock cycle, double, triple, and quadruple. Okay, so this is the first victory that we got from our experiments. Now what we have seen that whenever our instruction belongs to this group one. Group one is the instructions that have single clock cycle to execute. The signatures are quite similar. They are not exactly same, but they are quite similar. So just by seeing the acoustic signatures, we were able to distinguish the instructions into four categories. But when we are going to the instruction which is in the same category, just these acoustic signatures were not helping. Okay, so what we did is that, so basically when we are going to run a particular program, they will not have single instruction, right? So our code will look something like that. So first we create profile for every instructions, and then we run the whole code and try to understand that these signatures are mapping with any of the profile instructions or not. Okay, so what we have found out that we were getting the correct group but not exactly the correct instructions. Then what we try to do is that we try to use machine learning algorithms. Okay, mostly even more than machine learning algorithm, what helps us more is this: finding out what are the features of the sound signals that contribute more to categorize one instruction from the other, not only in the group, okay, but also very specific to a particular instruction. So we write an assembly code in Arduino Uno, then we record the audio for the code, and we did multiple repetition to get an average. Then we move this recording to the PC. Now we convert the formatting using VLC media player, get the recording into our audio data store in MATLAB. Okay. Now we extracted all the audio features. So MATLAB have nice tools to process audio signals. Okay, so you can use it. It's much better or clearer than the audio processing tool that is there in Python. Okay, so now what we find out that using this MR algorithm, minimum redundancy, maximum relevance, whoever works on machine learning, they're very aware of this particular MR algorithm. There is another algorithm named PCA. They also can rank the features of a particular signal and tell us that what are the most valued or what are the most weighted feature that can contribute to uniquely identify which particular instruction is running currently on my Arduino board. So what we have found out that we can use spectral centroid and sprayed, spectral flux, and mill frequency spectrum coefficient. These three features were most important features of the audio signal that were helping in uniquely identify a particular instruction in a single group. Okay, so we actually used these features to fit in a binary decision tree for multi-class classification. and then find the classification loss and lot confusion matrix. Okay, using this methodology, that first you collect the recordings, then by doing a time domain analysis, understand that whether these instructions are single clock cycle, double clock cycle, triple clock cycle, or quadruple clock cycle. Once the grouping is done, then you feed it to the MRMR algorithm to collect these three particular feature and their weights, and then run a multi-class classification. It can be any algorithm. Uh, Actually was giving us the signature of the particular instruction. So this kind of finding out what instruction is running on an algorithm or in a hardware platform is called instruction set disassembly. Okay, it can be used for defensive security as well as can be used for offensive security. So if I'm using this instruction set disassembly for offensive security, I can understand what code you are running without even touching your device. Okay, and also for defensive security, if something else starts running in your hardware, the acoustic signatures will change. Basically, when we run malwares, we try to do hijack the memory. So suddenly, if you see that a lot of memory load, memory stores operation are happening in your Arduino when it is not at all necessary, you must understand that there are some malware or ransomware is running. So suppose you are doing, suddenly you see that the encryption encryption, lot of files getting encrypted, so the signature will be different, acoustic signature will be different if you are doing some kind of like sensing and actuating operation. Okay, but if you see that an attacker is if the attacker want to capture this sensor data and try to lock it to do a ransomware attack, you will see a lot of signature of encryption algorithms. Okay, so normal sensing and writing data to the memory will be different from multiple fast encryption algorithms. So signature will be different, and our acoustic side channel can actually help us to do a classification between what is intended to run and what is actually running into the hardware. So now you say that this Atmega 32 is very primitive. So I'm not going to the result. Results are around first for the first run we get around 84%, and now we have a advanced methodology for which we are now getting around 96% accuracy. So it was very basic first result that we have got. But yes, if you can identify what are the instructions that are running in your computer with in your processor with 84% accuracy, if you can distinguish 84% instruction, that is also severe enough. So now currently what we are doing in our lab is that we have replicated this attack methodology for Raspberry Pis. Raspberry Pis are widely used in many IoT applications, many cyber physical systems, and if the attacker can understand that what are the instructions that are running in your Raspberry Pi, so then it will be problematic. So in Raspberry Pi, we have ARM processor, which is much complicated version, much complicated than Atmega, and we can actually we are getting good results. We can do an instruction set disassembly in Raspberry Pi as well, in ARM processor as well. Okay. Now, the next thing that we have done is that this Raspberry Pi or this Atmega, they are all single core processor, right? So currently our PhD students, what they are doing is that they are trying to understand that whether can we do instruction based disassembly for multi-core processors. Okay, because then every core will have different signatures, but the signatures will come together, right? Both will, I mean, the signature will be different, but they will be jumbled up. So can we separate the acoustic signatures from each other, from each core, and can understand that what code is running in which core? Okay, so then all these mobile phones and these laptops, they will be in very much danger. Okay, somebody can actually tap the fan that is there in the laptop, and the sound that this fan makes can also be used to understand what is happening in your in your hardware. So we are trying to understand that whether this acoustic based instruction disassembly can be done for multi-core processor. Can we do application or activity identification? So we are currently doing a location change detection in iPhone using acoustic side channels. Okay, or what are the background application that is running in your phone while you are talking into your phone? So we are able to do that kind of identification, that whether your Google Map is running, whether your Facebook is running, or whether your Instagram is running, whether you are any camera app is running. So all these signatures, acoustic signatures, are different from each other, and using acoustic side channel you can actually detect it. And finally, what we are trying to do is that can we build up a metric to understand how much information a system leaks through acoustics. Okay, every, as I say, every processor has different uh, emanations of sound. Sometimes acoustic can help somewhat, sometimes acoustic can may not help if there are too much of noise. So we want to understand that how much information is getting leaked, or how much privacy is getting compromised through acoustic. Okay, so these are the takeaway. We are currently working on them. So far, anybody has any questions? Is the main concept is clear? That was my intention, to make you introduced to the topic. Is there any question? No. Okay, very good. Okay, so now I'm going to something different. Now we will talk about timing side channel attacks on network on chip. Uh, First of all, any of you are heard of this network on chip term? Okay, fine. So, what is network on chip? Let us understand this first. Okay, so nowadays, uh, because we need a lot of faster execution of our application, what is happening is that we are coming up with something called MPSoC, multi-processor system on chip. So we will have a PCB which will be a system on chip, but it will have multiple processor inside it. Okay, so the very basic diagram of MPSoC look like this. We will have different IP cores. Okay, they can be processors, they can be memory system, they can be a Bluetooth module, they can be a wireless, Wi-Fi module, and then uh, they will be connected to the network interfaces, and these network interfaces are connected to these routers. These purple ones are routers. Okay, so the request can be generated by the different IP cores, and those through these routers and this network, they will go to different IP cores. So for now, in our systems, we have this bus structure, right? We have address bus, we have data bus, and we have control bus. Okay, so we have a processor which might have multiple core. Okay, but we have a processor, and then they are connected to the memory through bus system. But here what will happen, that these buses will be connected to each other through networks and routers. Okay, so if suppose I have two processor and currently this processor is busy, my request can go to the other processor through this network. So that's why it is called network on chip. Okay, so it's a very fascinating new domain. People are now coming up with different NOC architecture and the router design for this kind of NOC platform. Security currently is the least important, as with any other applications. Okay, so people are now developing network on chip. Qualcomm is working on network on chip development, but security is not a concern. But as a researcher, we are uh, started seeing that how this network on chip can be vulnerable to timing attacks. So our traditional microarchitecture, traditional processors are already vulnerable to timing attacks. You might have heard of this Spectre meltdown attack on Intel processors. They were microarchitectural attack, which actually exploit the cache hits and cache miss in the system to understand what are the secret operation that is happening. Okay, so since 2012, there are a lot of network on chip timing attacks have come up, like baseline attack, distributed timing attack, Cornock attack, and all, earthquake attack, P plus P arrow firewalk microprocessor firewalk attack. So this 5-6 very strong attacks, timing and timing plus cache exploitation has come up in the literature. But so let us see what, before going to the details, let us see what is the timing vulnerability in network on chip. Okay, so as we have seen that how timing attacks occur, that we send a plain text to this cryptographic module, we get the ciphertext, and the attacker can actually find the time that may needed to execute this operation. Now, if these operations are dependent on the secret key bit, okay, if they are not constant, depending on the whether it is a 0 or 1, this variation in the timing can tell us about the secret key. For example, if the key bit, suppose my key is 128 bit, okay, now if the key bit is 0, ith key bit is 0, I will do something. If the ith key bit is 1, I will do something else. And if these two timings, because we are doing different operation when the key bit is 0 or key bit is 1, if they are different, then the difference in the timing can tell me what is the secret key. So see, again, we are not breaking this algorithm as such. Okay, we are just trying to understand how the algorithm behaves differently when a particular key bit is 0 and when the particular key bit is 1. And if we can understand this particular nature of timing utilization by the hardware, we can get the key, right? We are not interested in the math. Okay, so this is what we call as timing attack. Now, let us understand that how network on chip work. Okay, suppose I have this 4 IP cores. Just I have explained what is IP core, right? So suppose I have 4 IP cores, IP core 0, 1, 2, 3. Okay. Now, B wants to send some request from IP core 0 to 3. If there is no issue or the routing path is clear, so that the request from B to 0, IP core 0 to IP core 3 will go directly. Now suppose while application B is sending a request from IP core 0 to IP core 3, application A in IP core 1 also wants to access service of IP core 2. So what will happen now is that application A has generated a new packet for some request in IP core 2, and there is a congestion at IP core 0 because now the router at IP core 1 has to pass both this packet, right? One will go to 3, other will go to 2, but they have to pass through IP core 1 because the structure of the network on chip is like this, 4 cross 1. Okay, so now what may happen, that the router will pass this A's data first and then it will pass B's data. Okay, so initially the time that will be needed for B to reach IP core 3 is different from when there is a congestion at IP core 1. So the timing difference is coming from the congestion in a particular router in the network on chip. So it's not now the execution time difference in the algorithm, rather when we are sending packet requests from one code to the other, how much time it is taking depending on the bandwidth of the network, that timing information is getting utilized by the attacker to launch an attack. Okay, I think the idea is clear that why network on chip is vulnerable to timing attack. Okay, now suppose this particular P processing element is running RSA algorithm, which is a cryptographic algorithm. Here is an attacker which is residing in processing element or PE1, and PE2 is nothing but a shared cache. Okay. So now in RSA, generally, if the algorithm is not constant time, then what happens is that whenever a key bit is 0, squaring operation happens. Okay. When the key bit is 1, then squaring and multiplication operation happens. Okay. So now suppose this processing element will definitely have its own L1 cache. Okay. Is the idea of L1 cache L2 cache is clear to everybody? Can anybody tell me that what is L1 and L2 cache in computer organization? Okay. Do we know about memory hierarchy? Anybody? Okay. But we do have computer organization course, right, in computer science? Uh, okay. I guess not. Okay. But yeah, it would be great to have a computer organization course because it is very much important to know how the computer looks like from inside. Okay. So what happens in computer organization is that we have a processor and we have three different levels of um, memory hierarchy. The closest memory is what we called as cache, which is first the most closest is the general purpose register that is attached to the processor. Okay, then we have cache, which is the size is very small, but the access time is very fast. Okay, then we have main memory. Okay, the access time is medium, but the size is much larger than the cache. And then we have the hard drive or the secondary memory. So cache memories are generally made of something called SRAM, static RAM. That's why they take very small amount of because the SRAMs are basically made of one transistors. Okay, so that's why they take very small place to hold one bit of information, but they are very costly. That's why we use small part of it. It's costly in terms of that to store this cache memory. We need to give a lot of constant power supply. That's why it is costly. Then comes the main memory where we use something called SRAMs are made of 6 transistor, DRAMs are made of 1 transistor. Okay, so so that is cheap, but it's the access time is not very fast. Okay, then the hard drive can be made of like Blu-ray or magnetic tape. Nowadays we have this SDD cards and all, so their access time is much more than that. Now even this cache are divided into two parts, L1 cache and L2 cache. Now in L1 cache, what happens is that L1 cache is a subset of L2 cache, and L1 cache is divided into two parts, L1 data cache, L1 instruction cache. So the instruction that are going to be processed by the processor will go from the L1 cache part of the instruction, and the data on which the instruction will be processed will go from the L1 cache part of the data. Now L2 cache is basically the amalgamation of the both code and data. Okay, so what happens in network on chip is that, sorry, here these processing elements will have the processor as well as the L1 cache. Okay, but it's a very small in size. So now suppose when the RSA is processing and request, if the data is not present in this L1 cache, this L2 cache is a shared cache which is used by all the processing element. So it can ask for a squaring operation value retrieval from L2 cache. It can also ask for a squaring and multiplication value from the L2 cache if it is not present in L1 cache. So if there is no congestion in these routers, the attacker can capture the timing for this squaring and multiply operation if it is getting accessed from the shared cache. Now, if the attacker is creating congestion in the path, this value will change. Okay, so finally, the attacker can understand whether the RSA is asking for, or the PE0 is asking for a 0 operation related to 0 or 1 if there is congestion in the network. So this is how the attacker can retrieve the secret key without even mathematically breaking the RSA in network on chip. So this is the simple example that I have given you. But given this particular design, you have understood that the attacker has to lie between this sensitive path between the target processing element and the shared cache. Okay, so now here the adversarial model for such attacks is that the attack target the MPSoC with network on chip architecture having any kind of the bus topology. It can be mesh, it can be torus, it can be flattened butterfly, ring, point-to-point topology, whatever, with different kind of routing algorithm. What is which are basically XY or YX algorithm. Let us tell you what I mean by XY or YX. Suppose this is a 4x1 network on chip. Okay, so here it will always increase in x axis. Okay, but suppose I have a 4x2 network on chip, and now instead of only 0, 1, 2, 3, I have also 4, 5, 6, 7. So suppose I have generated a request in 0 and it has to go to 6. What will happen in XY algorithm? First it will go to 0, 1, 2 and then come down to 6. Okay, so that is X and then Y. And in YX what will happen? 0 to 4, 5, 6 in this fashion. So that's the YX algorithm. So XY algorithm or YX algorithm, they tell how the data packet will proceed in a particular network on chip. But what happens is that the how it will follow the packet, it is predefined. After you have fabricated your network on chip, you cannot actually change the routing algorithm. Okay, so the attacker needs to know the topological order, but not the routing algorithm. So the attacker must know whether it is a mesh topology or a torus topology or a ring topology, but routing algorithm can be anything. Now the attacker can control one of the P and run a malicious program like remote access tool on the MPSoC that gets allocated to one of the P. Okay, so the attacker will not know which PE it has been assigned to. It will just run a malicious program, and this malicious program can be assigned to any one of the PE. Okay, so now once the malicious program is run in one of the PE, then the attacker can actually tap into the network and understand the throughput of the network. Okay, so which P it will get allocated to, it is not in hand of the attacker. Okay, so now the malicious program gets allocated to the P by the mapping algorithm employed for the program allocation on the MPSoC. The attacker needs not to know which P the program gets allocated. And the attacker should have the ability to communicate to all the Ps on the MPSoC either by requesting an appropriate shared cache block that maps to the LLC bank attached to the P, or by crafting packets containing proper destination address of the required P. Now, attacker can concurrently send ping requests to multiple Ps in the MPSoC, recording the response time of each sent request. So now we propose something called door knock attack to understand the MPSoC layout. Why it is important? Why attacker needs to know the layout of the MPSoC to launch a timing attack that we have actually discussed. The one that we have shown, one in P0, the RSA is running In PE2, the malicious attacker is there, and in PE2, the shared cache is there. So why it is important for the attacker to know the layout uh, of the MPSOC? Any educated guess? Anybody? Even if you can see this diagram that I am showing, you can have a guess. Okay. Okay, so the reason is because, as I have shown in my previous slide, the attacker has to be in between the sensitive path, between the target P and the shared cache. If the attacker does not reside into the sensitive path, then this simple timing attacks cannot be launched. Okay, the attacker will create a congestion in some other routers, but it will not impact the RSA PU. Okay, so it is very much important to know for the attacker that it has got allocated by the mapping algorithm in the sensitive part between the PE, which is running this secret algorithm, and the shared cache. So that's why we proposed a door knock attack to reverse engineer the PE. The network on chip. Okay, so maybe the attacker has an information like this is a 4x4 network on chip. It has a ring topology. It is having a XY algorithm and all. Okay, but exactly in which P it will get allotted to, that is not known to the attacker. That depends on the mapping algorithm, and we cannot really forge a mapping algorithm. Okay, so if the attacker does not rely on the sensitive path, it actually cannot launch a timing attack. Okay, so we basically used timing information to understand whether it is in the critical path or sensitive path or not. So now, then once we know that we are in the sensitive path, attacker knows that we are in the sensitive path, then it launched timing attack to retrieve the secret key. Okay, so let's see how it will understand that with the layout of the uh, particular MPSOC. So in this diagram, there are four processing elements. Okay, PE1, then this PE, a malicious PE, PE2, and PE3. Okay, so now the mapping algorithm has mapped the malicious PE in this particular processing element. Okay, so every processing element has their own router to connect to the network bus. Okay, now what this particular P will do, the malicious P will do, it will create, first it will create a congestion in router 1 and simultaneously send ping request to all the processing element. So first it will create this contention with introducing bogus packets and then send ping request to P1, P2 and P3. Okay. So now what will happen that after certain time, PE1 will reply back to this P, PE2 is reply back to this P, PE3 will also reply back to this P. But please note, the same request will go from this PE to R1, then R2, then PE1, then R2, then R1, then PE, right? But for P3, it is P to R1, then R3, then R4, then P3, then R4, then R3, then R1, then P, right? So the time to get a response from P3 is definitely more than the time needed from PE1 or from PE2. Okay, so here the attacker will categorize this response time by keeping PE1 and PE2 in single set because their response times are similar, whereas PE3 into a different set. Okay, now the next point would be that the attacker still does not know that whether PE3 is connected to PE2 or PE1, right? It has just understood that PE3 is not an immediate connection to this malicious PE, right? Because it is taking more time. Okay, so now it has to understand that whether PE1 is connected to P or P3 or P2 is connected to P3. Now what it will do is that it will create a contention in R3, okay, and then send ping request to all three pins. So now there is no contention is R2. So the packets at PE1 will take the same time as it was taking in case B. Whereas the packet which was going to PE2 and PE3 will change because there is a new congestion in the R3. So the time for PE2 as well as PE3 both will increase. As a result, the attacker will understand that this PE3 is it's not connected to PE1, rather it is connected to PE2. Now you might have thought that why we are creating congestion only in R3? Why didn't we have made a congestion in R2? We could have. In that case, what would have happened? Only P2's time would have been delayed, and P2's and P3's time would have been same. In that perspective, also the attacker would have understood that P1 is not connected to P3. Okay, so this is a simple example, and this architecture is also very easy architecture, but we have replicated this attack for different topology and different kind of architecture. So we have 2 cross 2, total 4 P's, 3 cross 3, 1 cross 4, 3 cross 4, 4 cross 4. For ring, it is 4, 16, 8. For point to point, we have used 8 node, 16 node. For torus, we have taken 3 cross 3, 4 cross 4. For flattened butterfly, also we have used 3 cross 3 and 4 cross 4. We have even taken routing algorithms like XY and YZ, YX. For ring, we have used shortest path routing. So what we have seen that these many numbers of sets, the thing that we were talking about, set of sets are dependent on the timing response that we are getting from the P's. Okay, so these many number of sets were created, and with 100% accuracy, just by using ping request and creating contention in different routers, the attacker was getting the layout and in a 100% accuracy. Okay, so from here, that where the attacker is currently relying. Okay, so it can understand whether it is in a sensitive path or not. If it is not in the sensitive path, then it has to again run this, make the mapping algorithm run this RAT application and get placed in somewhere which decide between the sensitive path. But as you can see that when the number of nodes increases, the clock cycle that is needed to launch this attack also increases. Sorry. For example, when it is 2 cross 2 or 1 cross 4, the execution time is around 100 to 200. But when the number of P's are like 9 or 12 or 16, the execution time increases. Okay. But yeah, it will take more number of pings. That's why execution time will increase. But ultimately, it is such a simple method that we will be able to reverse engineer the layout of the network on chip. So we published this paper in IEEE Embedded System Letters, and now what we are trying is that how we can how can we integrate this reverse engineering attack with traditional timing attack to launch a key instruction in secure domains P's in the NOC. Okay, so we are trying to integrate this thing. And how can we develop an attack methodology where the adversarial P does not need to be in the critical path or the sensitive path? Can we still make a contention which will be useful to get the secret key value? And then obviously how to develop countermeasures for such attack. So you can look into these papers and this paper, and if it seems interesting, then you can actually do some research on network and chip security as well. What we do is that we do not right now we do not have a like a industry level NOC implementations. Okay, so what we do is we simulate network on chip in something called Garnet. Garnet is a tool which is very much used in computer architecture, microarchitectural simulation, and we use it to create network on chip. and on that we test our algorithms, attack algorithms, countermeasure algorithms and all. So you can do the same as well. Or there are a lot of on-chip router design code available in GitHub. Even if you are comfortable with Verilog code, you can actually run those on-chip routers in an FPGA board and create your own NOC. So we have some PhD students who are actually trying to build up network on chip architecture in FPGAs, and then you can run this kind of timing attacks and countermeasure in real in those FPGAs. So I think, is anybody has any question?
Ma'am, one question is has been posted in YouTube live link, and that
Okay.
is copied in the chat box, Meet
Yes.
chat box. What is the significance of rate limiting in mitigating door knock attacks?
What do you mean by Shivji? What is the meaning of rate limiting here? What rate? You are talking about injection rate of the packets. Is that so? If you are talking about injection rate of the packets, then I would say that there would be underutilization of the resources. Suppose in a router can process have a buffer of like four packets buffer, okay, and just to limit the rate of packet processing, if we use only two of them, okay, so then there will be underutilization and your MPSOC will underperform. So we don't want it. Okay, there is always a trade-off between performance and security when we talk about safety. But our target is to provide a countermeasure which will enhance the security parameters of the system without much compromise on the performance. Yes, there would be additional hardware to check whether there is an live timing attacks is happening or not. There would be complicated encryption algorithms, constant whenever we develop a constant time uh, implementation of a cryptographic algorithm, they take more time, more hardware footprint and all. So always there is a trade-off. So if we try to limit the data rate to stop such attack, the system will underperform. That is the problem. Okay, so now I will, if there is no more question, I will go to the next topic, which is hardware Trojan horses in approximate computing hardwares. Okay. So first of all, this paper we have published in VLSID 2022, and later on we are working on a lot of different aspects of approximate computing hardwares. We are trying to make data formats which are approximate computing friendly, so that we can use them for approximation that we use in image processing or in machine learning or in neural networks and all. So so in this fashion, I mean, approximation can be done in many layers. We mainly focus on the hardware level and the data format level. So today we will be talking about approximation in the hardware level and how Trojan can be inserted in a approximate computing hardware. Okay, just a second. Okay, so why we use approximate computing for hardware acceleration? Okay, so nowadays we have a massive data processing demands that is growing day by day, and it is actually making the computation very expensive. Okay, so people were thinking about design paradigm that is used for efficient computing without incurring more power consumption. So approximate computing actually enhance the overall performance of an error tolerant application at the expense of a bounded loss in the accuracy. So when we talk about machine learning accelerators or neural network accelerators, we can actually tolerate some loss of information. Okay, we do not need accurate value of the computation that we do in different, neural network. No. Okay, but also we have to ensure that, because in neural network we have a lot of layer, and if we do not give importance to error in the initial layers, then that will impact the other layers or the upcoming layers very, very badly. So with this, depending on how much tolerant an application is with respect to the error, we can actually reduce the accuracy a little bit, and that actually help us to gain a lot in terms of power or efficiency. So that's why we basically deploy approximate techniques in the design of ML accelerators. So we approximate the storage, we approximate the circuit to make the calculations or computations fast and energy efficient. So now, suppose I have an accurate circuit of full adder. Okay, so you all have idea about adders and subtractors, right? How they are designed using gates and all logic gates. I hope that thing is there. So suppose I have an accurate circuit, I will give input 5 and 3. The output will always be 8. Okay, I give 2 and 7, the output will always be 9. Okay. But when we use approximate adders instead of accurate adders, what happens is that 5 plus 3 sometimes can give me 7.9, sometimes it can give me 8.1, but it will never give me 9 or 10 or 5 or 7. So what we are saying here, they are probabilistic in nature. It does not have a deterministic input-output characteristics, but it can reduce the resource consumptions or power consumption. Okay. So now, what is anybody aware of this hardware Trojan horses? Has anybody heard of hardware Trojan horse? No. Okay, fine. So let me give you an example. It was eye-opening for me when I was doing PhD in IIT Kharagpur. So one cab service, a leader of cab service company came to our department in our lab, and they said that uh, in their cab they wanted to add a circuit which will let them know that how long the driver is sitting on the seat of the car cab driver's seat, and how long he is not sitting in the driver's seat. Okay, that was the data they need to collect, so that they have changed the dashboard, and the new model of the dashboard were sent to China for fabrication. Okay, so these dashboards came back, and they deployed them into the car, and those cars ran in Bangalore city for 4 years. Okay, now after 4 years, they have found out that when the dashboards came back, there are a small pen drive, I mean, smaller than a small pen drive. There is a small component that had been added to the dashboard. Okay, which they had no idea. They have not given that specification to the manufacturing company in China, but they have added it. And what that particular small pen drive kind of thing was doing, whenever the car was going to a public Wi-Fi network where you really do not need a password. Okay, for example, that it is long back, 10 years back news that I'm telling you, maybe airport Wi-Fi or rail station Wi-Fi or some cafe Wi-Fi. What it was doing is that all this driver's information or the log of the from the car was passed to some unknown server um, through this public Wi-Fi by this particular small component that has been added to the dashboard. So this is hardware version of malware that actually can leak information from your hardware. That's why we call it as hardware Trojan horse. Now, what I have just give you an example of hardware Trojan horse in the PCB level, right? A component that has been added to your PCB, and it was very easy to detect if we have done some checking, if they have done some checking. But this kind of alteration on the device can be done in circuit level as well, and it's very difficult to catch those modified circuits. Okay, so generally, but it's not a new thing. There is a company called Microchip in USA. They were exposed to hardware Trojan horse attack. Again, credit goes to China, and there was a time they never accepted it, but their share market fell like anything because of that attacks, because their chip goes to Wi-Fi routers and whatnot, and all of them were actually were exposed due to this hardware Trojan that were injected. So as I was saying that when it is a accurate circuit, generally to check whether there is a hardware Trojan or not, we generate a conventional stacked fault or automated test pattern generation based testing to detect any modification. So these hardware Trojans are very trickily designed. They will not change the functioning of the hardware for every possible inputs. Okay, so they are meant to be triggered for very specific input that you rarely give to your circuit. And once that it gets that input, it will be triggered and it will start malfunctioning. Okay, so now you understand for an n input circuit, there are 2 to the power n number of possible input output patterns, right? Now, if this n becomes 128, for AES we have 128-bit input, 128-bit output. So it's very common. So your possible input is 2 to the power 128, right? And you are developing billions of circuits and chips, right? So it becomes very much exhaustive for you to check all possible input output patterns. So what we do, we automatically create a test pattern for inputs which are rare inputs that can be given to a circuit, and then we check for this rare input how the output is working or how the hardware circuit is happening. So these ATPG tools are used to generate these rare inputs for a circuit and check the behavior under the input patterns. Hardware Trojans can be one of these rare inputs. Okay, so it's very burdensome to understand out of these 2 to the power 128 inputs, which will be the rare inputs and on which one the hardware Trojan can be triggered, because we don't know how the hardware Trojan has been designed. Okay, so creating a hardware Trojan might be very easy given if you have the netlist, but detecting hardware Trojan is yet a huge problem and open research area on hardware security. Now you understand that our approximate circuits are anyway not giving me accurate value. So how much difficult it would be to find the rare inputs and to understand that whether the deviation of these approximate circuits are due to the natural inaccuracy that is there in the approximate circuit or due to some hardware Trojan triggering. Okay, so the proposed attack model here, because we are designing hardware Trojan for approximate circuit, here we aim to insert a hardware Trojan horse in block-based approximate adders that render them inefficient to cater error resilient application. Okay, so the target is that when I am creating a approximate adder circuit, the hardware Trojan will behave like it is a natural inaccuracy. But when I'm going to use this adder for an ML accelerator, they will degrade the performance of that particular application. So at the verification level, we are not going to catch the hardware Trojan, but it will slowly degrade the performance of the application. That is the target. And we will see how we can do it in approximate errors. So as I said that this particular work is very specific to block based low latency approximate adders. So what we have here is that we have n blocks of k-bit summation blocks. All these summation blocks are k-bit adders. Okay, so we give k-bit input to k-bit input and we get k-bit output. Okay, but what is the difference? In the summation blocks, we have these full adders, and then these full adders will generate some carry. Okay, but we will not wait for the carry to be generated. We will predict the carry and pass the carry to the next summation block. That is where the approximation comes. Okay, so the idea is that suppose the actual carry is 1 at the end of this summation block I minus 1. If my carry prediction logic predict it as 1, then I will get the correct result in the next summation block. If my carry prediction logic, because it is probabilistic in nature, gives me a 0, then what will happen? That there will be some error in the summation value. Okay, so that is where the error is coming into the whole calculation. But these carry prediction logics are generated in such a way that it will not render to a huge error. Rather, it will create a small error that is tolerated by the application, right? So now, let us see how hardware Trojan work. So, suppose this circuit. Okay, can anybody tell me what this gate is? This particular gate I am showing over here. Can you see my browser cursor? Can anybody say which
XOR
gate
gate,
this
XOR
is?
gate.
XOR gate, right? Okay. So there is a XOR gate, there is a OR gate, and there is a NOT gate. Okay. So ideally, if I have this XOR gate, then for 0, 1 and 1, 0, I should get a 1. And for 0, 0 and 1, 1, I should get a 0. So C should be 0 if the inputs are same, and the C should be 1 if the inputs are not same. Okay. Now, suppose the attacker wants that whatever be the input, I want this C to always give me a 1. Okay. So the attacker can do what? It can add a NOT gate first, that whenever the output of the C will be 0, it will flip the bit and then pass it to a OR gate. Because it is flipping the bit whenever it is 0, it is always giving 1. The output of the NOT gate will always giving 1. And it now does not depend on what is the value of actual C is, it will always give us C as 1. Okay. So now you think of a 1-bit full adder. This is the circuit of a full adder, and we add this part here. Okay, we do it. Now, how the circuit will malfunction? Whatever will be value of the C in A and B, the summation bit will always give you 1. Okay, so here for half of the inputs, so the summation bit was 1, and for half of the input, the summation bit was 0. But here, the summation bit will always give you 1. Okay, so this is the hardware Trojan that we are going to insert into our NK bit block adder in the block approximate adder. Okay, so now the idea is that one of the 1-bit full adder among the cascading full adders get replaced with tampered 1-bit full adder containing this hardware Trojan horse. So there are total NK full adders, N into K full adders in this circuit. Now I have to understand that which 1-bit full adder I am going to replace and how to ensure that this Trojan get masked in the complete design. Okay, so the position of placing this hardware trojan in a particular tampered 1-bit full adder is a challenge. Okay, we have to place it in such a way that the error tolerance at the adder level should be within the limit, so that nobody can understand that there is more to the natural error that this approximate error is generating. Okay, but when we will use them in calculation of an ML accelerator, then they will degrade the performance. Okay. So the impact of the Trojan is that since the tampered sum is always 1, it is wrong in 4 of the 8 possible cases, right? This way, the output of the tampered full adder wrong with probability half. However, this is only when the input carry to the full adder is unbiased. Okay. Now, if the input carry is itself biased towards 1 with probability p, then the final output get biased with the probability 1 by 2 by to the power p, which is much less than 1. Therefore, the output of this 1-bit full adder is wrong in some rare cases. So that is what I was saying, that the hardware trojan is triggered for very rare number of input patterns. So because this probability is there, it is actually aiding us to hide or to mask the hardware trojan. If it was totally a accurate full adder set, then we would have uh, captured this hardware trojan very easily. Because if a hardware trojan is getting triggered by half for half of the inputs, then it is very easy to catch. But because of this probabilistic nature of approximate adder, the probability gets down from half to the power p. So that is how it becomes a rare case. Okay. So this is a trick that we have applied to create this hardware trojan. Now, any one of the 1-bit full adder can be replaced with this tampered 1-bit full adder. Okay, so now the desirable choice of the attacker would be that the error produced post trojan insertion should be bounded, and it should significantly damage the end application result. So if the error is bounded in the post production, then the test tool will not able to detect it. But because it is actually for 4 out of 8 inputs to that particular full adder, it is giving me wrong result. It is going to impact the application. So we have actually followed a hit and trial approach to get the suitable trojan insertion site across varying architecture of block based approximate adders. So here we have architecture of 8-bit summation block, 16-bit summation block, 32-bit summation block, and we have such 4 blocks. Okay, so 8 cross 4 full adders, 16 cross 4 full adder, 32 cross 4 full adders are there. Okay, so now what we have seen, that for all this architecture, if we tamper block number 1, then the masking will be there. That means the post trojan instruction error that is produced, it is bounded, but it was also not affecting the application. Okay, but if we add the trojan in the second block, masking was there, error was bounded, but the application result was affecting. Okay, now again, if we insert the block first 1 or 2, but insertion region is the MSB side, then the error was unbounded. That means post production, the people can actually detect that the approximate adder is not working. So the application result was affected. So our target is that error has to be bounded, but application result has to be affected. Okay, so we are achieving that from the LSB side. If we tamper the second block of any one of the adders, then the error will be bounded, but the application will be affected. So we used uh, this Gaussian smoothing thing. Just a second. Uh, these are the different block-based adders, various designs. So their area power delay were like this in the range of 50 to 60, 30 to 40, and 0.33 to 0.54. After the tampered measure, when we have inserted the hardware trojan, see the areas are not changing much. 54.22, sorry, 52.4 to 52.6. 60.11 to 64.26. Okay, 67 to 68. The tampering is very less. And in power also, the power consumption is almost same, 40.44 in watt to 44.94. Okay, 33.42 to 33.21. Okay, so delays are same, 30, 0.33, 0.33, 0.3, 0.3, 0.37. So the post-production quality analysis is not giving us much. It is not telling me that okay, there is a hardware trojan, it is taking more power, more area, more delay, because we just used additional two gates. That's it. In this whole 32 cross 4 adders, we have just used two extra gate. But now when we come to the pre and post HKS insertion in Gaussian smoothing, what we are seeing is that PSNR is degrading like anything. See, 26.29 to 19.42, 33 to 25.73. Okay, SSIM, these are the quality metric of a Gaussian smoothing, 0.7876 to 0.6421. The lesser the number, the quality is less. Okay. So this is how, although the area power delay metric is not giving us much hint about the hardware trojan, the quality when we use these adders for Gaussian smoothing application, the quality is getting reduced. Okay, so this is one result we have shown. There are many other results for DNN accelerators also, and there also we are saying that the application is getting affected a lot. Okay, so the final takeaway here is that how to make approximate hardware more reliable, how to make the approximate hardware protected against hardware Trojan horse, and then side channel can be used defensively or offensively for approximate hardware security. Okay, so I think that's all from my side, and now I am open to the questions. Any question, anyone?
Participants, if you have any question, you can write in the YouTube live chat box, or those who have attended through Google Meet, please write your query in the chat box of Meet. I think participants do not have any query, any question. The chat box is overwhelmed with nice session, very informative session. Thank you, ma'am. The participants have enjoyed a lot your talk. So,
Madam, I have a very small point. Actually, it's not a question. That if uh, uh, if we can invade from the outside to a chip, to a hardware structure, its PCB block, its internal gate pattern, if we can invade to that level also,
Yes.
then how security remains at all? I mean, maybe those hardware systems you can, I mean, definitely you can, I mean, you can visualize all these things, but as an outsider, I think then where is the security? If we can reach up to that PCB level, that gate level, so and this is my curiosity here.
See, security, though I work or research on security, you cannot attain 100% security at all, ever. Okay, it is always like a cat and mouse game. Okay, so uh, these hardware level attacks are very hard to do. It's much more easier to crack onto your database by using an SQL injection attacks. But it's not. I will not say that it is not possible. And this supply chain, IC supply chain has become so big. It has so many parts, so many third party vendors are involved. We talk about Intel is processing chip, but I mean, we have no idea that how many other parties are involved when this final laptop that you are getting is finally ready to be used. Okay, there are innumerable number of companies that are involved, and it's very hard to understand whom I trust and whom I not trust. Okay, so currently in USA there is a chip act that is coming up. So many research friends in USA, in University of Florida and all, they are for the long time asking the government to use a technology called microdot in ICs. It will be like a small dot kind of thing, but it will help you to understand that whether the chip is fake or not, the chip is aged or not, this kind of thing. Okay, so for example, today, if our laptop has certain problem, many of the time we do not go to the authentic vendors. Okay, and that is a huge issue. That is a huge issue because in Apple laptop, the motherboard is gold coated. Okay, and there are a lot of pirated version of such Apple motherboard. Okay, so you go to a unauthentic service center, they will just replace your motherboard and replace it with exact replica of it, but without the gold coating. But that is why
it means during the manufacture, during the development phase, it could be tempered. I mean, if we can develop in that way.
Yes, definitely it could be tempered. So then we have to be vigilant. So we have to be like as much checking as we can do. Okay, maybe we cannot be 100% foolproof against attacks, but nowadays if you go to the market and if you see that there is a router which costs 5,000, and there is another router which is costing 10,000, but it is giving you WPA3 security, okay, certification, maybe you will go by the 5,000 rupees because it is causing you less money, but that they are vulnerable to attacks, right?
Yes,
So
ma'am.
people has to be very much aware of the security vulnerabilities that are there. Otherwise, it has to be a very much a ground level effort from every one of us to make the IC supply chain secure.
The complete chain of this manufacturing process should be under surveillance. Because
Exactly.
who is
Exactly.
putting which hardware structure in what pattern, what kind of Trojan they are feeding, so we don't know.
Yeah.
Thank you, ma'am. Okay, ma'am. Thank you.
Okay, then. So I think we can sign off now. If you have any question, if you want to know more, you can write me an email, and I would be happy to help. Thank you.
Thank you, ma'am. We have come to know about different types of attacks and security threats throughout the session, and also about hardware Trojan concept, which is totally new to us. On behalf of everyone here, I would like to extend my sincere gratitude to Dr. Urvi Chatterjee for sharing such valuable insights with us today. Your expertise, knowledge, and engaging presentation have certainly enriched our understanding, and we are truly thankful for the time and effort you have put into this session. We are sure that the lessons learned today will have a lasting impact on all of us. Thank you once again for being with us and inspiring us today. Now, as a gesture of honor, we are presenting a certificate to Dr. Urvi Chatterjee, which is displayed on the screen, and we request our esteemed speaker to accept the same.
Yeah, thank you so much. Thank you. Yeah.
Thank you, ma'am. And uh, thank you all the participants for being with us. And our next session will be started tomorrow at 10 a.m. sharp. All are requested to join the meeting on time. The YouTube link will be shared in the WhatsApp group tomorrow morning. Thank you. Thank you for your patience.
Thank you, ma'am. Thank you.